Let's look at these announcements. The homework assignment I've collected from you, and Lab 7, the report for that is going to be due on Tuesday next week. And you've got a new homework assignment coming up due on Thursday, the 16th of October, so that's a week from today. Did you not get the handout? Did you get it?
Yeah.
So what we're going to do today is actually spend the entirety of our class time working on some Euler's equation problems, because in the feedback I've received over successive semesters is that this is one of the concepts that students struggle with the most. And so the first problem we're going to look at is going to be a problem where we're accelerating an enclosed container of water. It's liquid water inside of this, and both the handout and the, oh no, it's not water, it's mercury. Okay, so specific gravity 13 point, what does it say, 5.6? 13.6? So the specific gravity of this mercury is 13.56. This container is full of mercury, and we are given that the vertical dimension between F and G is 87 centimeters. And we're given a vertical acceleration, A sub z, is negative 12.5 meters per second squared. So that means it's being accelerated downward. And we know the pressure at G. We want to know the pressure at F. So let's just, before I turn you loose to work on this with a partner or individually if you prefer, let's talk about just conceptually whether the pressure at F should be greater than the pressure at G or less than the pressure at G. If it wasn't moving at all, if it was just a normal hydrostatic equation type thing, then obviously the pressure at F would be less than the pressure at G. If it was being accelerated down at the same rate as gravity, if it was being accelerated down at 9.81 meters per second squared, then the pressure at G and the pressure at F would be the same, right? But since it's being accelerated downward, that actually means that the pressure at F is going to be larger than the pressure at G. So keep that in mind when you're plugging the numbers into the equation. Here I've expanded out Euler's equation in the z direction. You'll have to find the delta z between the 2 points, the density of the liquid, which is based on the specific gravity. The acceleration in z, remember, it's very important when we're doing Euler's problems to not only use the correct sign convention for what's considered up and what's considered positive to the right, but also it's critical that we correctly pick location 1 and location 2, because this has location 2 minus location 1, and then we've got the negative sign here, and we're being careful about putting the negative sign into the acceleration, so the order of everything is going to be important. And so looking at F and G,
So let's accelerate 2 ways down into the right.
that's right, it is. And so to find the pressure at F, it actually doesn't matter what the sideways acceleration is, but it does matter what the vertical acceleration is. And so you're going to solve this problem in 2 steps. You're going to first find the pressure at F by considering the vertical acceleration, and then you're going to handle this question of what is delta x by considering the acceleration in the x direction, this A sub x, that's 15 meters per second squared. Okay, but what has more elevation, location F or location G? Obviously it's location F, and so we're going to label that as number 2, as location 2 when we're working in the vertical direction here in this formula. Now what about when we're working side to side, when we're considering location G and location H? Which should be location 1 and which is going to be designated as number 2? G will be which? Nope. 1. It will be 1. You had a 50-50 guess. Right. How do we decide what is 2 and what is 1? What's the rule for that labeling? Furthest one to the right will be location 2. Whatever has the most of 2. And when it comes to vertical, it's whichever one is above the other is location 2. So whatever has the most z would be designated as location 2 if we're working in the vertical direction. Whatever has the most x is going to be designated as location 2 when we're working horizontally. All right. So with those, question? You don't have to subtract the gravity from it. Gravity is taken care of on this side of the equation because gamma z2 and gamma z1, that's going to take into account the effective gravity because gamma, remember, is the unit weight, it's the unit weight, but it's density times g. So you don't need to have like 9.81 minus 12.5. You'll put the actual acceleration that the body is experiencing over here in a sub z. All right, so work this. Another question?
Sorry, it says here negative acceleration on z direction. Does that mean that it's actually accelerating downward?
Yeah, it does because our sign convention is to call up positive z, and our sign convention is to call to the right positive x. And so if something was accelerating to the left, then we would say a sub x is negative. And if it's accelerating down, we'd say a sub z is negative. In this case, it is accelerating down.
And you say that f in that case is 2.
What?
F would be number 2.
That's right, because f has the most z. It's above the other location. All right. Okay, so I'm going to turn you loose. Let's solve this one and then go over the solution to make sure we're all on the same page. Be sure and write the name of the people that you worked with on that page in addition to your own name. I'm going to collect this at the end of class and give you some homework points for the work that you're doing today. Okay, so we worked the vertical acceleration and the vertical pressure differences first. Expanding out Euler's equation where the L direction is z because our acceleration is in the z direction. And here's the expanded version of Euler's equation. And we're going to call the elevation at location g, that's our datum, our elevation datum. So that's elevation is equal to 0. So that gamma zg term is going to cancel out. And we can rearrange the equation to solve for p sub f, which is what we're after. Just move the remaining zf term over to the right-hand side, the p sub g term to the right-hand side, and so on. And then from there, it's just plugging in the numbers and being careful about the sign convention. Remember, we have to put the negative value for the acceleration in here. And so we have the 485,000 pascals, and then subtracting this 115,731. Well, what is that related to? That is related to gamma ZF. And so this is kind of like, you could call it the hydrostatic effect. If there wasn't any additional acceleration vertically, then the pressure at F would be lower than the pressure at G. And this is how much lower the pressure would be at F if it was only gravitational effects that were going on. But we know that actually there is this other acceleration that's happening. And so this part of it is taking into account that downward acceleration. And it turns out that the downward acceleration actually overcomes the effect that would be that hydrostatic component. So the minus negative 147,465 means that there's actually a net pressure increase as we go from G to F. So the pressure at F is greater. Now this is only true as long as that is being accelerated downward at negative 12.5 meters per second squared. As soon as the acceleration changes, so is the pressure profile. But at this instant, where the acceleration is downward at negative 12.5 meters per second squared, then we can find out what the pressure at F will be relative to the pressure at G. Euler's equation is confusing. You got to be really careful about sign convention and direction to make sure that you don't lose track of that negative sign. That's not a minor error if you forget it. That's a major error. So any questions on that part of it, finding the pressure at F? All right, so then the other part is looking at, if you know the pressures, they must be some certain distance apart, because we know there's an acceleration in the x direction of 15 meters per second. We know the pressure at both locations, but we don't know the distance between them. And so it's just rearranging Euler's equation to solve for some unknown delta x. And you can see that I've gone through the algebra, rearranged. The delta x is going to be the pressure at h minus the pressure at g, divided by negative density times the acceleration in x. So the distance is going to be 1.7945 meters. Any questions about this one? All right, well, let's take a look at the second problem. We've got a truck, and it's partially filled with a liquid. And it says in the handout, what does it say what the liquid is? Does it say water? All right. So it's water, and the container is 18 feet long and 7 feet high, but it's only partially filled with a liquid. We know about the truck that it'll never speed up or slow down at a rate more than 8.02 feet per second squared. So if it's accelerating to the right, which way is the liquid going to slosh? It's going to slosh to the back, to the left, right. And when it's slowing down, so when the acceleration is to the left, then the liquid surface will slosh to the right, and the water level would be higher up here. So the question is asking, how deeply can the tank be filled without spilling? Can I actually see that? Let me take it. I used to ask a follow-up question, but I think this semester I'm just asking you that. It's a little bit, thank you, it's just a little bit of geometry here, you know, how deep the water is. If it's really deep, and then you start that accelerating, then it's going to spill out the side. So you need to find out the maximum depth that can make sure that it's not going to spill for this given acceleration. So here's the deal. When you're done with that and you're confident in your solution and your solution looks good, then you can just turn it in right here, and that's it for today. We're not going to have any other examples or any other lecture besides that. If you'd like to take a look, if you think you've got it, but you want to check answers, ask around, see if you can get a consensus from the classmates you're working with. I can take a look at it and give you the thumbs up or the thumbs down. I may not tell you exactly where your error is because I want you to get the experience in finding those. But yeah, that'll be it for today. So when you're done, you can set it on the table and have an early lunch.